Hi, this is Scott. I really appreciate our sponsors because they make the show possible. Today's show is sponsored by Developer Express. Become a UI superhero with Dev Express controls and libraries. Deliver elegant .NET solutions that address customer needs today. By leveraging your existing knowledge, you can build next-generation touch-enabled solutions for tomorrow. You can download your free 30-day trial at dx.hanselminutes.com. That's dx.hanselminutes.com. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and today I'm talking with Dr. Krysta Svore. She is the research manager of the Quantum Architectures and Computation Group at Microsoft. How are you?
I'm great. Thanks for having me on the show.
Well, thanks for coming on the show. It's overwhelming to even think about something like quantum computing, and I appreciate you being available and being so flexible in talking about this. I've actually been watching all of your videos and YouTubes and reading articles and trying to get my head around this because the word quantum is one of those words that I think we, the lay people, attach a lot of mysterious and mystical things to. So I wanted to talk about it in a very concrete way. Is there a quantum computer yet?
Well, that's a great question. Yes, quantum computers exist today, actually, and really they've been around in a very small, early form for several years now. And really, our goal now is to see a quantum computer scale up. Right. So we have these preliminary quantum computers. They can't do anything more powerful than your classical computers. But as we scale them up, the promise is that on certain problems, they're going to far outperform what we can do with your typical processing, your conventional computing. The conventional computing you have today. So some problems that you would want to run and solve using conventional computers, even if that's, say, a supercomputer, some problems will actually take billions and billions of years to find a solution. And these, some of these problems with a quantum computer, a scaled up quantum computer, you'll actually be able to solve them in a matter of hours or days. So that's a pretty substantial improvement.
Does that mean that it is and again, all my questions are going to be ignorant, so just assume I'm saying, forgive my ignorance in front of everything that I say.
Sure.
Is that because the quantum computer is faster, or is it because it's taking shortcuts?
Yeah, it's a very nuanced change here. So when we say faster, the clock rate of the quantum computer actually isn't necessarily faster than your conventional computer clock rate, right? You're looking at something that might be maybe 100 nanoseconds, 100 nanoseconds up to a microsecond for a clock rate. That's not faster than conventional clock rates. But the key is that when you look at the algorithms, right, the applications that you're going to run on a quantum computer, the number of operations in those algorithms or in those applications is so much fewer, so much less than the number of operations you would need to do on your conventional computer. That indeed the ultimate runtime to find the solution is much, much faster.
Interesting. Okay, so that makes me feel like maybe a quantum computer isn't a generalized thing. It's more like a GPU or a coprocessor for math.
Yeah, exactly. We like to think about quantum computers really as an accelerator, right? So imagine Azure, right? I work at Microsoft, so we have Microsoft Azure. We have this amazing cloud computing platform. And what do we bring to the cloud? We bring to the cloud many different types of processing and compute options, whether that's GPU, FPGA, CPU, right? And another one of those options is going to be your quantum chip, your quantum computer, your quantum accelerator. And so indeed, you're not going to run every problem you want to solve on a quantum computer. You're really going to target it for a special class of problems or for a subroutine within your algorithm. You're going to design algorithms in a hybrid way. You might use your GPU for some data processing and then send that data after that to your quantum chip, right? So you can really operate in this hybrid, this hybrid compute environment.
Mm. It seems to me like the industry and the Wired magazines are kind of going nuts because it's just so fun to say quantum. It's just one of those mystical words, and they're making big statements around how this is going to change everything. And because so many of us have been in tech for so long, it feels like every 20 minutes there's something that's going to change everything, whether it be AI or ML or is it going to change everything, or do you think the hype machine maybe is going too far?
I think it's going to change quite a lot. Everything might be a little extreme, but I think we will see revolutionary level changes coming from being able to actually quantum compute. The types of problems we're looking at solving with a quantum computer are, I believe world changing. Right? We're looking at solving things that really give us more knowledge, about how to better, more efficiently produce food or, combat things like global warming. These are no small scale problems. We're looking at problems that the human race needs to face and solve. Quantum computers can help us find solutions to this level of problem. Of course, we'll do it in conjunction with our conventional computing and supercomputers and everything else. It will be a hybrid style solution, but quantum computers will be a key, absolute critical piece to finding solutions for this scale of problem.
There was a time when I would buy a 386 SX that didn't have a coprocessor, and Excel would use it or not use it depending on whether it was there. And there was a time when I could buy a Voodoo graphics card and get better graphics or not. Right. Will there be a time that I'll be able to go and buy a card and pop it into my machine and it'll have, a quantum coprocessor? Or do you think this is something that's going to be relegated to giant refrigerators in the cloud?
Yeah, I think more and more we're moving to more of a cloud-based model across compute more generally, right? Because you're going to have your data stored in the cloud, you have apps and services in the cloud, and then, you need not buy the chip or the card to put into your, local PC. You can access an amazing set of resources in the cloud. So I think ultimately we're seeing a move to, broader and broader cloud compute. And in that environment, of course, will sit these quantum chips that you will have access to. It is also the case that a quantum computer, at least most of the paths to realizing a quantum computer, including the path we're taking at Microsoft, indeed, the quantum computer is operating in a very low temperature environment, millikelvin temperatures. And that means we need what's called a dilution refrigerator around it. So popping a dilution refrigerator into your local PC probably isn't going to happen. And that's
it's
another
water
reason.
Cooling to the next level.
Yeah, exactly. But, it definitely having access to those devices in the cloud, that will make it accessible for everyone.
Interesting. Now you have a PhD, but you also worked in machine learning and things like that. Are quantum computers and machine learning intermingled, or is that just your career path?
Well, yeah, it's pretty remarkable. I did a PhD in quantum computing, and then when I joined Microsoft, I studied and did research in machine learning for web ranking for several years. And at that time, that was over a decade ago, I didn't yet see the crossing between the two opportunities that I had taken with quantum computing and machine learning. And now it's such we're really looking at quantum machine learning. So it was it was great happenstance that I studied both of these subjects. And now we're really diving into what will quantum computing bring and lend to machine learning and AI. What does quantum mechanics bring to machine learning? How can we take cues from modeling and computing, the type of modeling and computing nature does, how do we take those cues and build better models of vision, speech, language, text, data, right? Can you take something that fundamentally has some quantum mechanical elements to it, say a quantum model? Can that quantum model better represent data or bring new insights? It's absolutely fascinating that now with a quantum computer, you really have a better glimpse into how nature computes. And with that, it's fun to think about the promise that brings for machine learning. So indeed, now quantum machine learning is an area that we're definitely investigating quite a lot, and we see improvements coming from quantum models of data. We see speed ups, ways to better train deep neural nets. You can get faster training of models. You can get better approximations of data and so forth.
So you said something really powerful in the middle there where you said how nature itself computes. I've heard a number of people imply, or not more than just imply, say that nature is a big computer. Now, this isn't necessarily the Elon Musk we're all in the matrix theory, but the idea that in order for nature to simply be, it has to calculate. And it seems like quantum computing is trying to take some of that spare CPU, for lack of a better word, and do something with it.
Yeah. So yeah, you can think of nature as a big computer, right? Its clock rate is much faster than the quantum computer. But indeed, with a quantum computer, what you're able to do is really simulate physical systems, right? At the core, what are we doing? We're evolving what's called Schrodinger's equation, right? Which tells us how state evolves, how these quantum mechanical states evolve over time. And by being able to actually model that and compute, make it digital even, make it able to be error corrected, we're basically getting a step closer to being able to take a computational, hammer to some of the problems that nature is solving every day. Things like we think about quantum chemistry or materials. Nature, you go outside, you see things are growing, right? Trees are growing, leaves, you have grass and flowers and all of these things are growing, right? And nature's just doing that. Now, if we can understand better how we produce, how does nature produce fertilizer? How do they perform what's called nitrogen fixation so efficiently? We don't perform nitrogen fixation in the lab near as efficiently as nature does it with microbes in the ground. But now with a quantum computer, we can begin to actually study these microbes, understand how do these organisms actually produce fertilizer so efficiently, and then try to model that, mimic it, engineer it, and then come up with a much better procedure. Just that alone, studying what we call nitrogen fixation, the process that we use to produce artificial fertilizer, with that, we actually could end up saving something like 3% of the world's natural gas. Today, we use something like 3% of the world's natural gas just to produce artificial fertilizer in labs. So if we can make that more efficient, that could be huge. So that's an example of modeling nature, right, with a quantum computer.
Right. And looking at like the idealist view of the nitrogen cycle and doing the right thing to make it go effectively, as opposed to artificially manufacturing fertilizer and plugging it into that cycle.
Yeah, see if we can engineer an artificial system, actually, a catalyst that really mimics what nature does in that process.
You mentioned Schrodinger, and as most laymen, myself included, know about the Schrodinger's cat concept, where you put the cat in the box, the cat is either alive or dead, and the theory is that there's a quantum superposition where for a time, the cat is both alive and dead. Is that something that's just come into popular culture, or does that theory or that concept really model a real problem that quantum computing tries to solve?
Right. Well, yes, the cat, of course, is a very macroscopic object. But indeed, the idea behind Schrodinger's cat, right, the idea that you have this black box, right, you have this box, and if you don't open the box, right? Inside the box, the cat is both alive and dead. But when you open the box, the cat is either alive or dead.
Mm-hmm.
The whole idea of this is it's really what's happening at the information level in your quantum computer. So inside your conventional computer, your classical computer, as we call it sometimes, are bits, right? Binary units of information. They can be 0 or 1, right?
Mm-hmm.
Your conventional computer is like it has switches. They're on or off. Now, a quantum computer inside has qubits, quantum bits. And these quantum bits can take on, just as you just said, what's called a superposition of states, this alive and dead notion. The superposition of states, what it means is a qubit can be both 0 and 1 simultaneously when it's operating inside the quantum computer. Now, the catch is when I look at my qubit, so I measure my qubit from the outside world, from our macroscopic world. I want to get information out of my, out of my quantum computer. I measure the state. It becomes 0 or 1. And it becomes that with a probability associated to what's called the amplitude of the state, which goes into more detail than we probably want to get into on the podcast. But the whole idea being, it really is inside the quantum computer. It's like having all of these cats, all of these Schrödinger cats operating together. And then at the end of the computation, we measure the system and we get out a state.
So if I had 8 cats or 8 bits all in a row, are they alternating between all possible states and all potential 8, 256 or whatever 8 bits is worth of states, and then at the end, by observing them, I force the universe's hand, and then it gives me a value.
Right. So, if you remove the word alternating, so it's not that it's oscillating or kind of doing a path, then another path, then another path. It's actually doing it in parallel. So, inside the quantum computer, you have 8 qubits. Those 8 qubits, as you just said, you have 2 to the 8 actual states then, 256 states. And your quantum computer is simultaneously operating across all of those 256 states.
So all of the answers are existing at the same time until we force, and again, I apologize for using these terms that I'm sure are incorrect, but until we force its hand or we observe it, and then it is the observation that causes the universe to make the decision.
Exactly. So as soon as we measure, so to observe it, we measure the system, and when we measure it, we're saying, give me back out a class, one of these states, one of the 256 states. And it'll come back to me in a bit string, right? So I get that bit string back, but I get only one of the 256 states back when I measure the system.
So how do you know it's the right one? Again, all of my knowledge of this is entirely based on watching Black Mirror. So maybe I'm not prepared to interview you. But does not that mean that I have no way of knowing if the answer I got back is the right one? Because there could be 255 other Dr. Svore's that are out there enjoying their answer, which is different.
Right. So at the surface, it seems that way, right? But what's pretty remarkable is that you can design this algorithm. It's like, when you create a recipe to bake a cake, right? You could say, I'm going to throw all these ingredients together and I don't know if it's going to come out chocolate or vanilla or, but we don't really do that, right? We design the recipe so that we make a chocolate cake, right? The output ultimately needs to be the chocolate cake and not the vanilla cake. Here, same thing. We are going to design the algorithm just like we design classical algorithms, just like we design algorithms for our conventional computers. We have an idea of exactly what output we want. And so we set up the sequence of operations to optimize for getting that output out. And we can do that in the quantum computer as well. And what this comes to is an idea of what's called interference. Quantum interference, what we're really doing is, if you think of these states, right, in the example you gave, 256 states, right? Imagine them each as a wave in a tide pool. And when waves collide, they grow, right? The amplitude increases. some waves will grow and some waves actually will cancel out and disappear, right?
Mm-hmm.
And so just imagine, touching your finger to a tide pool and then touching your finger again and watching these waves collide with some growing, some collapsing. That's what we actually program, is to get some of these waves to increase in amplitude, in the height of the wave, and some of them to disappear. Now, if you imagine each of these waves as one of these states, that means I can get some of them to disappear out of the computation and some of them to really amplify. And as I amplify them, when I measure the system, the most amplified wave has the highest probability of being the state that I measure at the end. So if I can get my solution to be in that high amplitude wave, I'm pretty golden in terms of getting the solution out that I need. And every quantum algorithm then is a probabilistic algorithm. So if I didn't get the answer I wanted, or I want to check, I'm going to run the algorithm just a couple times, because with high probability, I'm going to get the state out that I want, because I've sculpted the solution, the algorithm, in a way that this high amplitude wave has the right answer in it.
That's interesting. That makes me think about, in the context of the many worlds theory, that how do you know that with the universe that we're in is the real one? It's because it's the most likely one, because we're in it.
Yeah.
If we weren't in it, it wouldn't be the most likely one.
Yeah, there you go.
Now, when someone says a qubit, I've heard people say that qubits are two states, like you said, where you can be in a superposition. But then I've also heard other explanations where one bit can contain multiple dimensions, for lack of a better word, like 24 or more different, up, down, left, right, and all these kind of things. Can you maybe explain that? Is that a confusion or an oversimplification? I heard Justin Trudeau explain that once, and it didn't quite sound right when he said it.
He did a pretty good job when he was interviewed on quantum computing, I thought. Yeah. So indeed, so let's go back to this notion of a quantum bit, right?
Okay.
Bit is base, two-level system, a binary system. So when we say qubit, we mean it's a two-level system. The qubit has two possible states, 0.
So it's still a bit.
Yeah, 0 or 1. But again, those states can be in superposition. So it's actually in the state 0 and 1, but it can take any combination, any linear combination of 0 and 1. So what this means visually is, think about a sphere, right? Like a ball. And imagine, the surface of this ball. What it means is, if I take this ball, say at the North Pole is the state 0, at the South Pole is the state 1. Now my qubit can take any point on the surface of this sphere, any point on the surface of the ball, that qubit state. So it could be just in the 0 state, it could be just in the 1 state, or it can be any combination of 0 and 1, meaning it could take any point on the sphere as its state. So it's still a two-level system. If you want, higher level systems, then you could go to we talk about ternary. Ternary would be a 3-level system, so a Q-trit. A D-level system, where D is arbitrary, is a Q-dit. But, most of the time we think about just qubits and mapping everything to binary.
So simplistically, if I looked at a sphere, my intuition might indicate that there would be more degrees of freedom than just those that between 0 and 1. I might think about, X, Y, and Z, but that's not necessarily the case, is it?
Well, no, indeed. You can think about it in more degrees of freedom. In fact, what is a qubit? It's hard to describe some of these mathematical principles on the podcast, but the idea being that let's take some value alpha and some value beta. My qubit can take the state alpha times the state 0 plus beta times the state 1. And alpha and beta are complex numbers. So we are operating, we didn't go into that on this sphere, but we're actually operating in a complex valued space.
Okay. And that is difficult not only to explain in 3 dimensions drawing a picture, it's even more difficult when you consider the fact that we're on a podcast that's moving linearly through time itself. So I appreciate your patience.
Yeah.
So these are the elements that we use, but I would not necessarily do all of this work in C#. I understand that there's a quantum developers kit that people can download, and I can program, the problems that I want to with, I can think about them outside in C#, put the quantum appropriate things into the dev kit, and I can simulate that even on my laptop if I wanted to.
Yeah, exactly. We're really thrilled that we just released the Microsoft Quantum Development Kit. And as part of this kit, we've released a brand new quantum-focused programming language called Q#. Mm-hmm. And the whole idea here is that we need a new language because these principles that we've just been, walking through together, superposition, interference, right? This notion of qubits that take on these different states. We need a language that allows you to express these things easily and at a high enough level that you can bring together, different aspects of quantum computing and quantum mechanics together to make a solution for an application that you're interested in doing. So with the Microsoft Quantum Development Kit, we've put out this high level, very accessible language Q#, which builds on many of the ideas behind languages like C# and F#. So it should look very familiar. It's embedded in Visual Studio, so you get syntax highlighting, debugging. It feels very familiar to the developer. And then with that, inside the Quantum Development Kit, we've also released a whole set of samples, tutorials, libraries, right? So you have all these libraries at your fingertips that you can pull together and call on to actually build a quantum application for a quantum solution for an application you're interested in doing. Plus, we have tutorials. So if you want to learn, gosh, how does quantum teleportation work? We have a whole sample, and it's written in Q#. The language is well documented, so you can walk through and begin to develop some intuition around quantum computing. And the hope is that by making quantum computing accessible to a broad audience, we're going to see just amazing solutions come out of the community in terms of what will we do with a quantum computer and what will the key killer applications be.
Mm-hmm. One of the things that I was a little overwhelmed to hear was that if I was going to do local work, 30 qubits takes about 16 gigs of RAM, 31 qubits doubles the memory. Right.
So what's great, I should also mention in the Quantum Development Kit, and you mentioned this earlier, is that it not only comes with the language and the samples, but also a target simulator. This simulator allows you to simulate what would happen on, as you just said, 30 qubits in roughly 16 gigs of RAM. Now, doubling, again, going back to the state space, one more qubit requires doubling the amount of memory. And so locally, you're looking at, around 30 qubits for simulation, which, again, that's released as part of the kit. But as you go to, say, 40, 41, 42 qubits, you're looking at running on, we've released a state-of-the-art simulator in Azure to allow you to run on that scale. Because after all, when you get to just 230, 250 qubits, you're looking at scaling to more memory than there are particles in the visible universe. So when you think about that, 250 qubits sounds so small, but the amount of information in 250 qubits is more information than we could store in particles in the visible universe.
But you're talking about simulating a quantum computer on a Surface Book. When I then run my code and move it from local into Azure, am I simply simulating it in Azure using their classical or standard computers, or is there in fact a quantum computer in Azure, or is it really that we're setting ourselves up for some theoretical future where there is a quantum computer in Azure?
Right. It's really that we're setting ourselves up to take the code that you're writing today. You can simulate it today in Azure. So you're simulating it within a classical computing, conventional computing environment using the Azure compute. And then that same code, when we have a scaled up quantum computer, that same sitting in Azure, that same code will then be able to be deployed on that compute in Azure on the quantum compute platform.
I see. So this is, so to oversimplify things, because that's what I'm so good at, it's like before GPUs, I might want to go and render the movie Toy Story. I could write all the code for some theoretical GPU. I simulate it locally, and it takes an hour for every frame. Fast forward 20 years, and now we could render Toy Story in real time on an NVIDIA card that we have on our PC.
Yeah, exactly right. I would say we're not on the 20-year time frame, though. The idea would be that this would happen in more like a less than 5-year time frame to really scale to a larger quantum application. And as we talked about in the beginning of the podcast, already today quantum hardware exists, and you're looking at small numbers of qubits, but the number of qubits we have today in the community is less than what you can simulate. So by being able to run on a simulator, say in Azure, that's giving you access to the equivalent of, like 40 qubits.
So let me ask one final question that I think will be a good way to end the show. For people who are listening, who might be going to work, and maybe they're doing, text boxes over data and not particularly amazing stuff from a quantum computing perspective, but they may have a problem that their business, whatever business they happen to be in, might need to answer. How does one know and determine that they have a question that is best answered by a quantum-focused language?
Yeah, that's a great question, and it's one that we continue to look into every day. I think some of the best problems to solve on a quantum computer are those where you're simulating a physical system, a quantum mechanical system. So, say you're working on thinking about things in material science. I want to think about an exotic property of a material. I want to think about catalysis. How do I make a chemical reaction more efficient? And if that catalyst and that reaction involves a heavy metal, then a quantum computer is a great candidate. Say I want to do machine learning, and I'm doing machine learning, but I have a way to maybe process data down. When we're looking at near-term quantum computers, if we have too much data, that's going to be expensive to do on a quantum computer. So cases where you maybe have streaming data or data that you could process down and then send to the quantum computer. For example, send a subroutine to the quantum computer to speed up your machine learning algorithm. And quantum computers are good, great at modeling the physical world. In many cases, they're great at doing finding quadratic square root speedups when searching for solutions. So those types of problems are things to think about.
Well, thank you so much for taking the time to put up with my questions and for educating all of us here on the show. We do appreciate you.
Oh, my pleasure. Thank you for having me on. And I encourage the listeners to go to Microsoft.com/quantum and try out the Microsoft Quantum Development Kit.
Fantastic. I am downloading it now. It integrates great with Visual Studio 2017.
Excellent.
This has been another episode of Hansel Minutes, and we'll see you again next week.